Good morning, Professor Grenfell's Math 12 Statistics class back again. This is Chapter 5, Section 3 on the binomial distribution. So here, a lot of probability distributions can be reduced to two outcomes, or a lot of probability experiments have two outcomes, or can be reduced to a case where there are only two outcomes. So, for example, coin toss, there's only two outcomes. Uh, some kind of sports game, two outcomes. You can say team A wins or team B wins. A medical treatment might have a lot of different effects, but we can reduce this to saying whether it was effective or ineffective in terms of treating a specific condition. And so here is the technical definition. A binomial experiment is a probability experiment, and it has to satisfy four requirements. There has to be a fixed number of trials. We usually call this little n. Each trial can have only two outcomes, or outcomes that can be reduced to two outcomes. So we discussed that, right? There could be a multiple choice test, and there could be four questions on there, four choices on there, but only one of them is right. So you can say you either got it right or you got it wrong. There's an instance in which you would say it's either a success or a failure, but it just says you can think of it this way. You don't have to. The outcomes must be independent of one another. And then finally, the probability of success must remain the same for every single repetition of this experiment, every single trial. In example 5-15, I've grabbed the screen here. It's asking us to decide whether each experiment is a binomial experiment. If not, say why not. All right, so part A is not. Well, let's read it first. Let's hang on 1 second before I exit out. Let's read. Selecting 20 university students and recording their class rank. This is still not a binomial experiment. There's no way to reduce this situation to only two outcomes. Part B, selecting 20 students from a university and recording their gender, is an example of a binomial experiment. So we would say yes, because there would be two choices. And we've selected these 20 at random, so there's no interdependence. They're independent from one another. There is the same likelihood throughout this population. Whatever the average is, we expect to select them within this 20 students. So they fit all of the requirements. Or rather, I should say, this experiment fits all four requirements for being a binomial experiment. In part C, notice that there are only two options because we are looking at only two potential outcomes, red or black. Sorry, I've forgotten to read it once again. Drawing 5 cards from the deck without replacement and recording whether they are red or black. So we have two outcomes, but because we did not put the cards back and then redraw, we have taken away the independence. So the ones that I've taken out are already out. And also, we've affected the probability. If we draw one black card out, then notice there's one less black card in the deck, and so the probability of drawing another black card or a red card would be altered. So here, this is not a binomial experiment. So in other words, C, that process or that experiment is not an example of binomial experiment because the events are not independent of one another. All right, next, D, selecting 5 students from a large school and asking them if they are on the dean's list. That would be an instance of being a binomial experiment. It satisfies all the requirements. And E, recording the number of children in 50 randomly selected families is not a binomial experiment because we are not asking if they have children or not children. We're asking how many, so there's too many options. So it's not binomial. Now, binomial experiment gives rise to a special distribution known as the binomial distribution. The notation is as follows. Lowercase p denotes the probability of a success. So this is a numerical value. We have to remember that we're reducing our experiment, whatever this probability experiment is, down to 2 outcomes. And we're kind of thinking this in terms of pass-fail, right? Success or failure. So we're saying well-defined what a success is, and then P is that numerical probability. Q is going to be the complement of that. That is going to be 1 minus P, and so that represents the probability, the numerical value, probability of not a success. So in other words, the other option. We've reduced it down to 2 outcomes, 2 options. N is going to be the number of trials that we run, and then X is the number of successes that we have when we run N trials. Now there is a formula for a function essentially that gives us the probability of getting exactly X successes out of N trials, and it only depends upon whatever we want for the number of successes out of how many trials and the probability of getting the success, because that, of course, gives us the probability of a failure. And so here, as we can see, this formula is horrible. So instead of using this, and what we will end up getting to do with the normal distribution in the future is we do not have to look at this formula itself because there's a nice table of values that we can utilize. So all of the examples that we'll be looking at will be utilizing this table of values, and I'll be referencing that. In example 5-16, we're talking about tossing coins. It says a coin is tossed 3 times. Find the probability of getting exactly 2 heads. And as you can see, I've broken this down as n equals 3 because we're tossing this coin 3 times. X equals 2 because we want to know the probability of getting exactly 2 heads. And P equals 1/2 because in this binomial experiment, we know that the theoretical probability of getting heads versus tails is 50-50. So it's 1/2 is a fraction value. And we pulled up Appendix A, the tables. This is Table B, page 770. And what we're going to do is we're going to go and find, here is n, and here are the various different values that x can be equal to. We're going to look at 2. And then across here on the columns, we're looking for P. P we have, oh, here I covered it up a little bit, is exactly 0.5. So we're just going to go ahead and line up this row and this column. And yeah, I scribbled over the bottom row, the row below. And so we'll do this calculation. Probability of getting exactly 2 heads would be 0.375 or 37.5%. So I'm sorry, I take this back. This was actually example 5-19 because they redid it and they used the table. So that's how we're going to be doing these. All right, I can't do 5-17 without grabbing another screenshot of the, I think the next page of table B. So we'll skip down to example 5-18. And this is a survey on employment. Sure. A survey from Teenage Research Unlimited, Northbrook, Illinois, found that 30% of teenage consumers receive their spending money from part-time jobs. If 5 teenagers are selected at random, find the probability that at least 3 of them will have part-time jobs. So there I'm just reading out of the example. And I'm going to go back through and just try to pick out what the given information is. So here, P, 30% have a part-time job. Okay, and we're looking for the probability that at least 3 of them will have a part-time job. So here, having a part-time job is the quality that we're looking for. So our chance of success is the chance or the proportion of the teenagers that have a part-time job. What else do we know? We got probability at least 3 of them, and we're looking at 5. All right, so it looks like N's got to be 5, and we want the probability at least 3 of them. Okay, right. So if we have 3, that's perfect. If we have 2, that's not going to work. So okay, got to count the other way. So 3 out of 5 have a part-time job, and that's fine. 4 out of 5 have a part-time job, that's fine. 5 out of 5, that's still at least 3. That's all of them, so that's at least 3. If we have 2, 1, or 0 that have a part-time job, then this event is not satisfied. So here we are going to be adding up some cumulative probabilities. So we just scroll back up here, and N is equal to 5. This tells us that we're going to be looking at this section right here because this was the N column, right? And X equals 3, 4, 5. That would be the probability of getting exactly, of having exactly 3 with a part-time job, exactly 4, and then exactly 5. Right, so we're going to be looking at this, this, and this, and adding up those 3 values. Last, P equals 0.3. We have to go up to the top here and find, oh, notice we have exactly 0.3. Notice here, if we don't have that exact proportion, let's say we had our probability of success was 27%, what we might want to do is either take the average of these 2 values or maybe err on the side of caution so that we don't make an overestimate. We choose whichever value out of these 2 columns would be lower. All right, but what we're doing is exactly this column right here. So we're going to be taking 0.132 plus 0.028 plus had to recopy really quickly before I forgot it. And so that adds up to a total of 0.162. So there's about a 16% chance that we'll have at least 3 with part-time jobs. Okay, let's do example 5-20, but please don't let anybody here make any jokes about my mother-in-law during the course of this problem. So this is a survey on fear of being home alone at night. And in a public opinion poll reported that 5% of Americans are afraid of being home alone in a house at night. If a random sample of 20 Americans is selected, find these probabilities by using the binomial table. So we'll go through these one by one. In part A, there are exactly 5 people in the sample who are afraid of being alone at night. Well, in this whole situation, we're selecting 20 people at random, and so those are our 20 trials, essentially. And the probability is the same every single time. So the only thing that is going to vary here is the value of x. So, as you can see here, we have n equals 20, these values of x, and here p is equal to 0.05. So we're looking at this column of this page of table B. And part A, we're just trying to find p of 5. What's the probability that exactly 5 people in the sample are going to be afraid of being alone at night? And so from the table, we have n equals 20, x equals 5, the correct value for p, and so the reading is 0.002. In part B, it says what is the probability there are at most 3 people in the sample who are afraid of being alone at night. So the key word here is at most. What does at most 3 mean? Could we have exactly 3? Yes, but that's the most. Could we have exactly 4? No, 3 is the most we could have. What if we had 2? Would that be okay? Let's see, is that more than 3? No, so 3 is the most that we can have, but we could fit 3, we could fit 2, we could fit 1. I don't know what it is that and where it's fitting, but when we say at most 3, we say that means less than or equal to 3. So here we have to add up the probability that are exactly 3, exactly 2, exactly 1, or no 1. And so we are going to be simply adding up these values from the table. Just want to say here, the complement of having at most 3 people, or in other words, less than or equal to 3 people, would be if you have 4 or 5, right? So here, another way that we could compute this probability, we could say the probability of exactly 4 plus the probability of exactly 5, that would be the combined probability of having either 4 or 5 people. And we'll subtract that whole thing away from 1. And so we find these values here in the table and add them together and then subtract away from 1. And so notice this gives us 0.985, which for our purposes we'll say is the same difference. If you said 0.984, or if you said 0.985, same difference, close enough. So that is within the margin of error. And let's see, part C is a little bit different. It says, what is the probability there are at least 3 people in the sample? So that would be greater than or equal to 3, not less than or equal to 3, not just the complement, not just 4 or 5. Here we're including 3 or 4 or 5. So let's write it like this. P as X is greater than or equal to 3. And that will break apart as P of 3 plus P of 4 plus P of 5. So we are simply adding up these 3 values, P of 3, P of 4, P of 5. So we have 0.060 plus 0.013 plus 0.002, and that gives us 0.075. Notice in part B, the book said, here, let's add up 4 numbers. And so I said, oh, okay, no, let's just add up 2 and then subtract it away from 1. And then in part C, the book said, okay, let's add up 3 numbers and then subtract that away from 1. And I said, no, let's just add up 3 different numbers and we'll get close enough. So they come up with, somehow they came up with 0.076 by adding up 3 numbers and then subtracting away from 1. But either way, 0.075 or 0.076, same difference. Now, we cannot leave this video without talking about the mean, the variance, and the standard deviation for the binomial distribution. So the mean is going to be computed a little bit differently. It's pretty easy. It's just the number of trials times the probability of success. For the variance, sigma squared, this is going to be NPQ, N times P times Q. So that's pretty nice. And then the standard deviation, sigma, is just the square root of sigma squared. But oftentimes we're just going to be using sigma itself. So we'll just say it's the square root of N times P times Q. In example 5-22, it tells us a coin is tossed 4 times. Find the mean, variance, and standard deviation of the number of heads that will be obtained. So here, and in all of these, where it asks for the means, variance, and standard deviation for a binomial distribution, all we're going to need to know is what is N, what is P, and what is Q. So in this case, they toss the coin 4 times, and we have a 50% chance of getting heads and a 50% chance of getting not heads, tails. Therefore, mu is going to be N times P, and that is 4 times 1/2. That gives us 2. The average number of heads that we would expect to see would be 2. Sigma squared, the variance, is, according to the formula, N times P times Q. Practice writing these down from memory. 4 times 1/2 times 1 minus 1/2 is 1/2. That gives us 1. And then sigma itself is just going to be the square root of the previous value. So don't compute it again. Don't do 4 times 1/2 times 1/2 again. Just do the square root of whatever you got there. And there it is. So let's move on to another example, a little bit more difficult. Example 5-23, rolling a die. It says this time an 8-sided die with the numbers 1 through 8 on the faces is rolled 560 times. Find the mean, variance, and standard deviation over the number of sevens that will be rolled. So here, it's a binomial experiment because we are saying, just count the number of times we get a 7. So the probability of success would be 1 out of 8. There's only 1 7 on there. And the probability of the failure would be 7 out of 8. Any of the other 8 faces of this 8-sided die would be a failure. Or in other words, not a 7. So the mean is n times p. So in this case, it is 560 times 1 over 8, and that would give us 70. The expected number of 7s that will roll should be 70. The variance, sigma squared, is going to be n times p times q, and then sigma is just going to be the square root of whatever we get from that. So this is 560 times 1 over 8 times 7 over 8, which works out as 61.25. And so then to find sigma, we just take the square root of 61.25, and that gives us 7.826.